Hey guys, welcome to this short video just to give you a little introduction to a couple more concepts, not necessarily ones that are guaranteed to be on the AP exam, but things that kind of tie into the stuff that we're talking about right now before we start getting into the fluid mechanics, the dynamics part of this with the moving fluids. All right, so first we're going to start off with a challenge. So before we go to this, I'd like for you to gather a cup of water or a bucket bowl, just a container full of water, and some paper clips. All right, so follow me to the table and we will try this challenge. All right, so I'm getting my daughters to help me out for this one. This one is a special kind of a challenge. I'd like for you guys to try it at home. All you need is a container of water. Okay, these are all the same. I use beakers so that it's clear so that you can see what's going on. You need a container of water and you need some paper clips. Any paper clip should work. Just, normal swirly paper clips like this. Don't use like the big binder clips or anything. Just use regular paper clips. Smaller ones will work, bigger ones will work. It's all fine. Okay, so the challenge is, can you make the paper clip float? All right, so all the questions have already been asked. Are all the containers the same? Yeah, these two are bigger than those. I only had two small ones. Is the liquid the same? Yeah, the water's, it's just plain water in all of them. I can do it in any of them. It doesn't matter. So take a couple minutes. I'll let you watch these guys try for a couple minutes, and then you try for a couple minutes. See if you can get a paper clip to float. All right, go for it.
Hey, mine's floating.
Hey, you made yours float.
Me too. Yeah, I knew it. I was right. My theory was correct.
What was your theory?
That you have to have like the same amount of I don't know what it is. I don't know the proper term. But you have to have the same amount of like distribution of the weight on all of the paper clip. Like something like that, but I don't know how to do that. I don't know how to explain it.
So I'm gonna have to cut out the first 10 seconds of this so that you don't see it work right away.
No. How do you put it on? Oh! Like, how do you put it on?
All right.
I'm telling you.
So here's the thing. Is the buoyant force enough to make the paper clip float? Right? In order to determine that, you have to decide which is more dense, metal or water. Do you guys know which is more dense?
Metal.
Metal is more dense. So if all that's happening is a buoyant force, the paper clip should sink. We actually need another force here. We need something else going on. Okay? What else is going on is something called surface tension. All right? So you'll notice that when they're really, really careful to set it on the top, now it's actually really hard to do it with their fingers. I'm actually pretty impressed that they were able to do it without with just their fingers. The easiest way to do it is to take a second paper clip and kind of fold it like this. And then if you'll set the paper clip on top, like that,
mine broke.
Then you can make sure that as you set it on the surface of the water, that you're not breaking the surface tension, right? And so you can see right there, congratulations, you broke my paper clip.
Two.
And it's pretty easy. You got to keep it flat all the way down. Okay? And it should float just like this guy. Okay?
Broke it again. I'm gonna do it properly.
There you go. Paperclip floating. It's just water.
No, mine dropped when I was
But the key is buoyancy is not enough.
Baby.
You've got to add in surface tension.
First try, baby.
All right. Once you do this, it should simplify.
Did you break all of
yours? All right. Now, hopefully that was interesting. That introduced us to the idea of surface tension. All right. If we were to draw a free body diagram for our paperclip, it should look something like this. Paperclip. Force of gravity, pulling down, and then force of the surface tension. There is no buoyancy there because it's literally on top of the water. It's not down in the water being pushed up. It's actually on the surface. So it's kind of an interesting thing in that we're not actually using any of the concepts that we've used previously. It's just the surface tension of the water. Now, obviously, depending on water's ability to do that, that will determine whether it's able to float on top based off of just the surface tension. It's not likely that you're going to have surface tension and buoyancy because surface tension is just a force at the surface, and then buoyancy is once you're actually submerged in the fluid and actually pushing some fluid out of the way. All right. Now, the surface tension is going to depend on a couple of different things. One of those things is something called cohesion, or the cohesive forces. Cohesive forces are forces between molecules of the same type. So that's like in water, due to the hydrogen bonding between the hydrogen and the oxygen. If you've done chemistry, you know that in a water molecule, the oxygen side is slightly negative and the hydrogen side is slightly positive. They're kind of attracted to each other. Even though the molecules don't combine, they are attracted to each other, those hydrogen and oxygens. And so what ends up happening is that we end up getting water molecules that are sticking together in something called hydrogen bonding. Now, that gives us a high amount of cohesion. All right. We also have something called adhesion, or adhesive forces. Adhesive forces are forces between molecules in different objects. And so that's between the water and the metal of the paperclip, or the water and the side of the glass. You may have seen this before. And again, if you think back to your chemistry days, whenever you looked in a test tube, what did you see? When you had liquid in there, there was always this thing that we called the meniscus, right? And you always measured this point right here at the bottom. What was happening over on the sides? Well, the water was creeping up the sides. That's because the adhesion, or the adhesive forces between the water molecules and the glass, were higher than the cohesion, the force between the water molecules trying to get them to stay together. If you'd use mercury, if you ever look at a mercury thermometer or something, or we were talking about the manometer the other day, the barometer that might have mercury inside of it. If you look at a barometer in which it has mercury, you would probably actually see something like this. You would see the barometer, which would have the bottom base like that, and when you looked at the mercury, it would actually look like this. It would kind of be an upside down meniscus. The reason why is because the cohesive forces of mercury pulling the mercury particles together is larger than the adhesive forces of the mercury and the glass, which again is another good reason why we use mercury inside of barometers and thermometers and things like that, other than the fact that it's more dense. So anyway, put those ideas together and you end up getting this thing which is surface tension, which is due to the cohesion of the water molecules with each other, and then the adhesion of the water being able to connect to the metal of that paperclip. Okay, so just some interesting ideas. Not anything to worry about long-term for AP, but kind of interesting things that we learn about here in connection with our fluid mechanics. All right, so at this point, you're done with your static fluids, and we're going to move on to some dynamic fluids. Move on to the next module.